Good morning, everyone. Before I start the presentation, I would like to acknowledge my co-author, Yuqing, Harry, Dan from TTCI, and Ali Tajaddini from FRA, and Brian Marquis from WPI Center. So today's topic is about real-world contact model and experimental validation by using the RCFS. So what is RCFS? First, give you some background information. Secondly, we talk about the new class model and comparison with test result. And thirdly, I'm going to show you something that surprised me during the test. Finally, we deliver the conclusion. RCFS, rolling contact fatigue simulator, as the name indicates, was built, designed by TTCI. We have been doing the test since 2015. You may be wondering, TTCI has almost approximately 50 miles of test track. We run the test every night, 1 MGT at fast. Why you still need this more test device? And we have 3 big buildings of the laboratory, test laboratory there. So this machine, test machine, is unique in terms of its almost fully controlled test conditions. At fast, there are so many things going on there, you don't know exactly what happened, and different from night to night and day to day. So the main purpose or the motivation for this RCFS is to investigate the root cause of RCF, of course. And in addition, there is a tribology study by using this controlled conditions test. And finally, and also most important, we want to validate the model we used during our research for all the business we did in terms of the simulation software real contact model or RCF model and wear model, you name it. So there's a video snapshot of the video showing the movement of those test rig. As we see from this plot, so there are full-scale wheel set and full-scale short track, both two rail installed on top of the table. And the wheel set only have 1 degree of freedom spin. That's it. No clearance, lateral, vertical. We use 0 clearance bearing. And but the table have 6 degree of freedom, 4 degree of freedom. It can basically, we allow it a lateral shift to adjust the longitudinal creepage and allow it to yaw to make what we designed as a lateral creepage. So we controlled both creepage by changing the position and the orientation. And the longitudinally is just back and forth longitudinal movement. It's different from a roller rig that is rolling. So it's more realistic in terms of the wheel-real contact like on the track. So it's from different wheel point from the camera, look at each of those locations that we are interested in. So what we did so far, basically summarized here. We measured the force, of course. We measured using instrument wheel set, instrument reel, and load cell from the machine itself. And we measure the force. We also do the static test to measure the contact patches, the imprint. So we get the force, we get the contact patch, and then we do the evaluation. Sorry, we do contact the stress analysis by using the program Professor Cocker developed the contact, and we get those stress we evaluated based on shakedown criteria. Of course, we do the methodological exam, and we also did the 3D surface image to analyze what's the surface roughness correlation with the contact, the crack, rolling contact fatigue. So we first talk about the static test. So showing here the imprint, contact imprint on the low rail. Basically, you can see the low rail is more or less a standard Hertz contact, one single contact patch. And the angle of attack effect is small. So 0 angle attack and the 10 milliradian angle of attack, you can shape 10 milliradians twist a little bit, but more or less is negligible. But on the high rail side is more interesting. Even on the tread, the shape is not Hertz contact anymore. It's the size we can measure, after the test very accurately, and the shape and the size. And when it's flange contact, shift lateral big enough, flange contact, then they're showing 2-point contact, one on the tread, one on the flange. And once there is a yaw angle of attack, it's showing the longitudinal shift on the flange. It's nothing special. Most of us know that. But it's interesting to see how those significant of longitudinal shift could be. 15 or sometimes could be even 40 millimeters longitudinal shift. So in the beginning of the test, we think we shifted, we do imprint, and then move the table, do another imprint. We think big enough for 20 or 30 millimeters. It ended up these still overlap a little bit when at the different test scenarios in terms of the lateral shift and angle of attack. So these several of them overlap together. This is for each of the test scenarios, but the flange contact started like 0.7 inch when the high rail, wheel rail clearance gap is disappeared. So angle of attack effect on flange contact is significant. So we get all those imprint by the static test. We want to simulate by using new cars. For those who don't know, new cars, it is a multi-body dynamic program for wheel control truck dynamic simulation. It was developed by TTCI over several decades, and over this several decade time period, we keep improving by using the test data to validate it. Whenever there is a chance, we want to validate it compared to new cars. So you can see the contact patch, even though the scale may be different, but you check there both have the scale there, so you can see the size actually how many millimeters. So it's matched pretty good in terms of the shape, the size, and the longitudinal shift distance. So the previous test, we do it dedicated for this benchmark purpose. We also, we do this rolling contact fatigue test daily, every day almost. And we have a lot of the RCF tests going on. So we pick up one of those tests. We do tests from the new rail to up to like 60K test in almost 2 weeks time. And some from brand new to kind of very conformal. We keep like different scenarios, lateral position and yaw angle. Do it, 60K. After 2 weeks, we get the result, and we also, every 2.5K, we measure the profiles, and we do the contact imprint. We compare it by using the new cars and the profile as the input. So when we compare them, you can see for the low rail test, from the beginning, and then as the cycle increased, it's get conformal, and contact patch bigger, and then even bigger from here is 20, eventually about 40 in the length of the contact patch. And you can see, those are pretty good match, but some of them, when it's get conformal, the test showing 3 isolated contact patch, but the simulation showing it's 3 merged contact patch together. And the high rail is more interesting, and also the shape changed over the different scenarios. And more or less, it's match the test result very well. We use the instrument wheel set to measure the forces. So at a different lateral position and different angle of attack, the big matrix, and we get all the forces, vertical, longitudinal, and lateral. So we compare these measured forces with nuclear simulation result for the quasi-static rolling conditions. So we match the result pretty good at the trend, but at flange contact, a little bit different due to the 3D contact effect. So what's surprising me is not this static test and the quasi-static rolling test, it's some of the transit tests. So this is the whole loading cycles here. So the table ramped up, touch the wheel, pull it constantly, load and the speed. And keep same orientation and position, and then ramp it up, and then repeat this cycle again. So let's do the RCF. But you can see, at a constant load and speed, the forces keep changing. And here show the 3 scenarios at different angle of attack. In the small angle of attack, the build up, the force has a slope, and at a higher angle of attack, the force gets flat. So what causes this slope? So first we think, the wheel and the rail is, everything is constant and fixed. There's no relative movement, so we think we control the creepage. Maybe the rail is under the force, the rail is deflection and the rolling and the lateral movement. So we design a bracket to hold the rail to make it very steady. It did change the result before and after, showing the magnitude did change a little, but the slope is still there. So what caused the problem? When everything is steady, is constant, why is there the slope? So we did more tests by compared to the lubricant conditions and the dry conditions. You can see as the lubricant friction coefficient is lower, it's more flat, and the dry condition is more slope. And this, we call this build-up of creep force. So everything is constant, and creep force still keep changing. And Carker, the theory, in his book, he talked about the transit creep force quite a few times. And but his prediction that the transit creep force build-up is only take 2 contact patch distance. But showing here, our result is like 10 times bigger than the distance until it reaches the constant speed. So the conclusion is clear for the first part. Nuclear's wheel-rail contact model works very well. And what surprised me is this creep force build-up phenomenon. So here's my way to show respect to Professor Carker by asking you a question. That if why our test results are not consistent with Professor Carker's prediction, if I'm wrong, where I could be wrong, and this needs to be further investigated. I want you to enlighten me from your experience. Finally, I would thank AAR and FRI for providing fundings, and Everest for providing test reels, and thank you for your attention. Sorry, it takes time.